Okay, so once we start up the process, then what we do is we actually operate this process, as I tried to say previously, for an infinite amount of time, unless there is a problem, there's a change we would like to do. So we continue the process from our process conditions. Let me do it this time. I'm going to run it for only 100 seconds. All right. Now let me show you the result. Animation. All right. Now we don't start with zero water level. It's going to start from the steady state value. Now remember, the steady state value was around 22 centimeters, right? So it's around 22 centimeters value here, and we are just making very small fluctuations around 22 centimeters. You can also see it here around 21.7 or something like that. We are making small fluctuations. Why do we have these fluctuations? Because there's water coming from here, and as you can see, there is a bug here. There should be water flowing here. And there should be water flowing here. Yeah, I'm sorry for that. In the next version, I'm going to, I hope, correct these problems. So inlet flow rate is changing all the time with small fluctuations. Still, we don't need that much of feedback control for the time being, and everything seems okay. Now, there is actually a condition for that. Even this very simple, or for any process, this may not be the case. I mean, even if there were small fluctuations, you let the system and it's going to make small fluctuations, and without the control, it's going to stay as it is. No, that system should be self-regulating, or in other terms, the process should be stable, as you have probably covered in your process control course. If the process is unstable, it has a positive pole, then given any disturbance without control, the process, the output will tend to go to infinity, will explode, or whatever you would like to call it. But this is a self-regulating process, and for 100 seconds, it has run, as you can see, it just moves around this value all the time. So it is at steady state, and this is a typical operating point that you make your design calculations, your project calculations in design course, and also in the process control course, your operating point around which you operate your process. Okay, but usually in processes, we would like to make changes. And the changes, for some reason, for instance, for the industrial practice or for some economical reasons, we would like to change the water level in the second tank. We don't like this 21.7 value or 21.85 now here. We would like to operate the process at a different water height value. And how are we going to do that? We should be able to do that by changing this outlet flow rate, because this is the manipulated value. And remember the rule, when we change this value, this water height will change, which is going to affect the water flowing here, and this is going to affect the water level at this point. So here we are going to explore the so-called process dynamics. What do I mean by that? The dynamic relation between manipulated variable and the change of the water level, because that's what we are interested in. When I change this outlet flow rate, how will this change be transmitted to the water level in the second tank? And what do I mean by how will this change, or what do I mean by the change being transmitted? There are two things. First of all, the time response. How will it respond with respect to time? A fast initial response, then a slower response. And at the end, when I'm a steady state, what is going to be the change corresponding to a certain change in outlet flow rate? What is going to be the corresponding change in the liquid level at steady state? And also in the dynamic phase, dynamic period. or the transient initial period. Okay, so here we have a practical problem in our case, and since we have the process, we can do any change that we like. And let me to give you an idea, I'm going to do the change here. This is the inlet, the outlet flow rate. I'm going to change this outlet flow rate to any value that I like. For instance, I can change this to, let's say, here when I do that, for instance, for the first 20 seconds, it's going to stay at 1. Then after 20 seconds on, I'm going to be changing to 0.81 liters per second. Now the question is, or what we would like to do is, we would like to explore the dynamics of the process. So what should this outlet be rate change from 1, where 1 corresponds to the current operating point, so that we can observe and understand the dynamics? Well, probably in your courses, in process dynamics course, you give a unit step change, but note that unit step, that unit just corresponds to the unit or the dimension of the manipulated variable that we are talking about here. If we had taken this as centimeter cube per second, then unit change would correspond to from 1000 to 1001. But if you take this at liters per second, then that unit change would correspond to from 1 to 2. So that word unit is actually pretty much, well, for mathematical analysis, of course, it's useful, but when it comes to practice, you should have an idea about the magnitude of a meaningful change on that outlet flow rate, so that you are going to obtain a meaningful response. And what would that be? First of all, we should realize something even before the magnitude of the change. The sign between the change in the outlet flow rate and water level here. Since the outlet flow rate, when we increase this, then this water level will go down, right? Increase the outlet flow rate, there is going to be less water here, right? So less water means less water pressure here. Less water pressure means less velocity here. Less inlet velocity here means less liquid level here. So when we increase the outlet flow rate, when we increase the U value, this Y value will be negative. So first of all, we should understand that. So change in U, delta U positive, then delta Y is going to be negative. That actually means Kp value is smaller than 0. And I'm talking about here the steady state case. For the theory behind that, please refer to CHE 475 course notes and groups and your instructor. Please go over the whole thing. So once we notice that, it's up to you, for instance, whether to decrease this value and see this increase, or increase this value, then see this decrease. But again, the problem is this: how much should we change this? So I'm thinking about maybe changing from 1 to 0.99 would be a good idea to start the whole thing. So let's do that. So where is my... All right, I'm going to take this value and make it 0.99. So after from 20 seconds on, I'm going to change this flow rate, the outlet flow rate, decrease to 0.99. Therefore, I expect there is going to be an increase here. Let's see whether this is going to be the case. And what I do is I start the process at this operating condition. That's the important point. So this condition, at this point, I make a change. So I simulate the system, and once I simulate it, I start my animation. Okay, let me bring the figures here. For some reason, the animations are shown in the other screen. All right. Now I have added these dash lines to show the initial operating point, so initial value. Now still the outlet flow rate is 1 liter per second, as you can see. Oh, down there is water here, this time. Still one, because time is 20, now is 0.99. Right, that the drop here after starting from time is equal to 20. Now, when we have less water here, there should be an increase in water level here. So let's see, then there's going to be a water level increase here. This seems to be slightly up, but down. I recommend you to have a look at this figure so that you get warmed up with the whole experimental idea. Then after that, you can always, I'm sorry, monitor the time trajectory in more detail. But just from this figure, can we see whether there is an increase or not? It is difficult. Again, even seeing the increase is very difficult, because since there is noise in our system, always some uncertainty and also disturbances, it is difficult to see whether there is a significant change from the operating condition or not, or is it just fluctuation. It seems to be a little bit above this level, all the time above these dash lines, whereas corresponding to the second tank, there seems to be no change here. So let's wait a little bit more time. I think I ran this system for 100 seconds, unfortunately. I should have waited, made it longer. I can do that. But the moral of the story is, well, as you can see, there is a slight change in the first tank. And maybe there is going to be, well, sooner or later, there's going to be also a slight change in the second tank. But here is the problem. Due to the inherent noise of the process, 0.99 changing by 0.01 liters per second seems to be too small. So a very small change in the manipulated variable yields a response that is clouded by the noise of the system, so that you cannot really clearly see the real signal here. Let me run the system a little bit longer so that you get the idea. So let me run it for 300 seconds, and then maybe we can have a better idea. Okay. Oops, unfortunately, this is going to be there anyway. I can pause the video here and later continue. That's a better idea. Okay, the simulation is over, and I just realized that this somehow sounds like those cooking programs. Once they start cooking and then they do all these preparations, and while cooking, they do not show the whole thing, they cut it and they show it at the end, and somewhat similar to that. Anyway, now as you can see, now we have 300 seconds, maybe a little bit longer I could have, but that's pretty much, I think the idea is clear. Now there's a slight increase here, right? You know, if you would like to see it more clearly, I can show it that way. Let's see, where did I draw it? I should have drawn it in a separate figure. Okay. So this is the response of the second tank. Actually, those red dots are this one. And this is actually, believe it or not, this seems like that exponential recovery curve, which is not exponential recovery curve, but some second, third order, some higher order response. But as you can see, it is too much noisy, and one cannot very easily extract a Kp and tau value here. And the idea is totally related with something that we have previously done in uncertainty analysis. If you recall that from the previous year, the idea is related. For instance, when we would like to find Kp value here, what we would basically do is Kp is going to be equal to delta y or delta h here for the specific question between steady state values and delta u value. And remember that there is no noise on delta u value. I have especially given no noise in outlet flow rate, so all the noise is in delta h value. And the trick point is this: if you give a small delta U value, the real change in delta H will be small. So basically we can write it as delta H real plus error over delta U. So when we would like to obtain a prediction for Kp hat, what we are going to do is we are going to be reading this delta. What we really need is this value. But what we are really reading is this value. Actually, this delta H real clouded by some random error term, some additive error, if we assume that this is the case. So we can write it as delta H real over delta U, which is the Kp real value plus E over delta U. So let me write it here again, Kp real, right, which we do not know, error over delta U value. Now here is the idea. If we would like this value as close as to this value, right? If we would like to make this small as it is possible, then we should make this value as small, as large as it should be, right? The delta H real, right, should be much greater than that additive additive error value. And if then we give a very small delta U value, delta H real is in the order of the error terms, the uncertainty, right? So there is a problem here. So if we had given a delta U such that delta H is 10 times greater, right? Then this part is going to be that Kp hat is going to be much closer to this real value, because delta H real is going to be delta H real plus error over delta U. Now we can still assume that the same E value is present there. Of course, delta U will change, but this value will also be much greater than compared to this case. Therefore, the value that we estimate is going to be much closer to the real value. So in other terms, instead of trying to obtain a Kp and tau value from this figure, try to obtain it from this figure with the same noise, but at a higher U value. Still the same fluctuations. Right, the magnitude of the fluctuations will be the same, but the change in y is going down. Y is going to be much larger here compared to this one, so that you can obtain an estimate of Kp more accurately. That's what I'm trying to say. Anyway, so that much of change of the delta U is not sufficient. So let's think about two guys discussing. One of them said, okay, let's use the smallest value. The other said is living on the other extreme. He or she says that, okay, let's decrease it to 0, right? Because it is the smallest possible value. If we go back to those specifications here, I have given some specifications, if you recall. Let's go back to those specifications. I said the manipulated variable can be between 0 and 2 liters per second. It cannot exceed 2 liters, and of course it cannot be negative because it's the outlet flow rate, right? Okay, so I'm going to come to that specifications again. So let's run it for 20, I'm sorry, for 0. Okay, that's great. Let's run it for again 300 seconds. That's sufficient. Okay, now I'm going to animate the process again. This time I would like to show you only this result. Then I'm going to show you the online figures. I think this is going to give you a better perspective. Let's see. Now after 20 seconds, for 20 seconds, it's going to be the operating point again. 21.7 centimeters here with 1 liters per second outlet. Then starting from 20 seconds, I'm going to close this valve. So therefore, water level here will be going up. And let's see what's going to happen. Now, as you can see, the up to time 20 seconds, we have outlet flow 1. So everything is a steady state. The dash lines show the initial values, and they are very much consistent with the actual values with very small fluctuations. Now we have dropped down this outlet flow rate to 0. Well, again, another bug here. I should have cut down the water here. Sorry for it. Now this starts increasing and building pressure here starts increasing, and this with some time lag it comes behind. Now the question is, would the pressure here be sufficient to prevent the overflow? That's actually a safety issue. A clever design would have seen that previously. No, it cannot do that. There is an overflow at 40 centimeters. Think about that. This is constant, and the rest of the water is going around. I couldn't do that, but this continues increasing. It is at constant 40 centimeters, and there's going to be a constant pressure here, and there's going to be a certain velocity, and this is increasing. Will it increase and cause an overflow? Actually, I don't know. Let's see. It may not be, because at 40 centimeters, the highest height, the highest water level is reached here. From this point on, it is a constant pressure inlet at this point. So a constant velocity here is that. So it all depends upon the velocity of the fluid. As you can see, I have not on purpose measured this value, right? Okay, but this seems to be not increasing, or increasing very slowly. Probably we are close to the steady state value. Actually, I can see the whole trajectory, and that's one advantage of the trajectory. You cannot see how much we are close to trajectory, but still you can see that there is a net overall increase, though very small. So basically from 22 to about 20, something like 28, we had an increase of 6 centimeters of water in about 100 seconds. And even this should give you an idea about the process, because we had totally closed the valve, full closure. And with full closure, this is the fastest response that you may obtain from this system. Now I think I can show you the other figure, trajectory. Okay, this is actually, as you can see, this is far from an exponential increase. Actually, the outlet cannot respond here during this time. It takes a very much long time compared to the increase of the water level in this tank until we have an outlet. And we reach 40, and we do not decrease from 40. Therefore, this opening is not wide enough to give an exit such that it's going to equilibrate 40 liters, 40 centimeters. But for the second tank, this inlet does not make it overflow, but I think it reaches 28 centimeters, 26, 28 centimeters, yes. And it is also here, 28 centimeters. It seems to be assuming a steady state value. And as you can see, the outlet flow rate is 0. Now, is this a desirable control? Well, it may be depending on the process, but one thing that in this case that we cannot use this is because this is not going to be a typical response. In a typical response, this tank will not overflow. Therefore, the dynamics that we see here is the overflow or a constant value reached here all the time, and that constant value gives a constant pressure and inlet velocity here to this tank. So this is not a typical response that we would be obtaining for any value. And more than that, for safety reasons, I do not want this to be realized. Let me go back to this case here. If computer does not crash, Yes, for the second tank, I would like H prime value to be between 4 and 40 centimeters, right? I don't want to reach 40 centimeters. So you are not allowed to run the system in this case. So you are not allowed this when you prepare or when you design your controller, you should not allow the overflow of this tank. So in either for safety reasons or due to the specifications of the question, but again, I think more important to understand theoretically, this is not a typical response that we would be obtaining it. In a typical response, this would correspond, this would converge to a steady state value, the blue lines, and that would make the red points also converge to another steady state value. Here, as you can see, we are far away from the steady state. If we let this system go, probably it would converge to steady state, maybe 60, 70, whatever, maybe higher than that, then the whole process will be different. So this is not a typical response that we obtain. Therefore, we cannot use this response to derive the process parameters, kp value, tau value, or dead time value. So this is also, as you can see, not a realistic change in outflow rate. So I think we have eliminated two possibilities, right, or two extremes. Changing by 0.01, you cannot beat noise. If you change it all the way, then the resulting response would be out of the operating conditions, and usually that will be the case for many of the real processes. And there would be another problem also related with changing the valve from one extreme to another extreme that I'm going to be trying to emphasize in a couple of minutes. You would be, well, it may be such that, for instance, I could have easily given the outlet flow rate, the minimum value, to be equal to 0.5 liters per second. So in this case, the smallest value that you could have used was 0.5 liters per second, and you could have used that value, and quite possibly, I'm not sure, but possibly the outlet would be between the outlet of the first tank, or the height of the first tank, would not exceed 40 centimeters, and everything would seem okay. Well, not exactly, because when you change the outlet flow rate from the medium to an extreme value, or between two extremes, you are seeing the dynamics over a very wide range. So what's the bad thing about that? I'll try to explain that in a couple of examples. Now, a more realistic case would be changing this flow rate at a more reasonable value. So that reasonable value may be, for instance, this is 0.90, because 0.99 was, as you can see, very, very low, but still 10 times larger than seems to be probably is going to work fine. So let's run this system, and let me run this system for 500 seconds or 600 seconds. If it's going to take too long, I can always pause the video and I can get rid of that part. All right, so it's going to run for 600 seconds. And let's animate the tank. So what I do is, starting from 20 seconds on, I'm going to shut down the valve from 1 liters per second to 0.9 liters per second. Therefore, I expect a change from an initial value of 21.7 centimeters to some higher value. And I'm going to record those values and try to come up with process parameters so that I'm going to obtain an empirical model of the process. That's what I'm going to do. So let's start the process. Also, let's only concentrate on the process at first. Then we are going to see the online monitoring schemes or graphs. Okay, so this is like watching or announcing a football game or something like this. As we can see, the water level is right now seems to be a little bit rising because we are at time 30 and the water level has dropped down to 90. Yes, this one is increasing. Therefore, this is going to increase also in a couple of minutes or in a couple of seconds, I guess. Let's see this increase here. As I said previously, think of these as a little bit large tanks, right, with large areas, cross-sectional areas. So it is difficult to fill them, and it's difficult to do the water level to increase. And 2 liters of water is just, think about 2 liters or 1 liter of water for drinking water, 2 of them in 1 second. But the area is so large that it doesn't affect the increase in water level that much. And this is too narrow, this pipes, such that the height or the increase in the water level in the first tank is a very slow change in the outlet volumetric flow rate, which really affects the second tank level. And there's, as you can see, there is a slight increase in the second tank. Okay, let me again pause recording and see later. Okay, the simulation is about to be over. And as you can see, the tanks have, of course, increased their heights, water levels. And with a step change, a negative step change in the outlet flow rate, we got a increase in height in the first tank, about a steady state change of 5 centimeters. I guess in the second tank, we are going to read it in more detail, hopefully in a couple of seconds. And these are more like the exponential curves that we would like to obtain. So let me get the whole thing in more detail. So for the second tank that we are interested in, this is the response that we obtain. Let's put grids here with some finer details, even finer. Yeah. And details in y-axis. Yes, I think that's pretty much sufficient. Okay, now let's remember the procedure. I think that would be even better. For the first 20 seconds, we continue with the steady state operation at 21.8 whatever, but starting from 22nd, we give the step change to the outlet flow rate. So we would be interested starting this point on. And starting from this point on, there seems to be initial kind of time delay, dead time region here. Then this seems like a second order, a higher order process increased to a steady state value. So I think the most practical thing that one can do here is approximately draw a straight line. I think that's pretty much okay. And I think 600 seconds is pretty much sufficient. A lower value probably will not be that much. Yeah, 500 would be also maybe sufficient. Even 400 may be sufficient. After 400, maybe there's a very slight increase in the average values. After, I think, 500, it seems to stabilize. In the presence of noise, it's a little bit difficult to exactly see what's going on, but I especially wanted to show you that. So we have that value here, and the initial value is somewhere here. Okay, and then we need to get rid of the period where we don't have any change in the manipulated variable. right? So this first 20 seconds is not something that we are interested in, because during this period, everything was, this first 20 seconds was the previous steady state value. Okay, what else? Now let's draw the process reaction curve. So the region with the curve, yeah, that seems pretty much okay. Yeah, this I think this is kind of tangent point here. Yeah, somewhat nice. As I said previously, since we have noise, it's difficult to exactly see what's going on. So this point is going to be approximately equal to, maybe we need even a finer. Well, that much fine reading is not that much important. Nevertheless, let me show it. Oops, if I can do. So it's going to be, I think, 35. So at that time of 15 time units. So let me write somewhere here, 15 seconds of that time. Then we are going to have another line. All right. And the reading here, oops, is going to be a little bit different. I think it's 119 is something like 167, something like this. So 197, I'm sorry, minus 35 is going to be the tau value, which is 160 seconds is tau. Okay. And the Kp value is going to be found as the difference in delta y over difference in delta u. So difference in delta y is somewhat like 23.93 or something, minus 21.85-ish. Yes, this value is going to be divided by the change in u value. And the change in u is, if I can write it, change in u is from 1 to 0.9. Okay, so this is minus 20.80. So let me write them here clearly. So the first process reaction curve test has given us these. Time delay is almost equal to 15 seconds. Process, have I read this correctly? Yeah, I think. Time constant is about 162 seconds, and Kp value is about 20.8. The unit is centimeter per liter per second. This is the delta U, and this is delta Y and delta H, because actually delta H is equal to Kp times delta U, but this is steady state value, so that's why it's called steady state. Anyway, so these are the values of our process when we change U from 1 to 0.9 liters per second. And the typical next step could be, since we have these d delta Kp and tau p values, let's use Cohen-Kuhn settings and find, let's use Cohen-Kuhn formulas and find the PI controller settings and finish the whole thing. Unfortunately, we have to include a couple of more things in our analysis. Let me go back to what I've written here so that I'm not missing anything. So I talked about these points here. Okay. Now, note that we have some suspicion about the linearity of this process. Now, if this process is linear, then from any operating point, any steady state value, when you give a delta U value of minus 0.1 liters per second, we should expect a change in delta H, which is equal to that value, which is equal to 2.08 centimeters. But is this process linear? And actually, well, there's reason to doubt that, but let's prove that this is the case and see what are the other possible process reaction curves that we may obtain under different conditions. I probably couldn't explain myself very clear, so I'd like to show you what to do next, and I think you get the idea. But before that, let me record these readings. Let me call them Y1. And let me write here Y1 so that I'm not going to forget what this is. So this result is oops, where's those results? Yeah, here. Okay, so these are, let me call them Y1 results. Now what I'm going to do is I'm going to give a similar change, but at a totally different operating point. If I have been operating the system at 1.5 liters per second and drop down the flow rate to 1.4 liters per second, would I obtain the same response? Let's see that. So in order to that, so what I'm going to do is this, I want this, check this, U from 1.5 to 1.4 liters per second, and I'm going to call this white. Let's see that. So I need to first operate at 1.5. So that way, these are just technical details to run the simulation. No big deal. So I need 1.5. And this region also should be 5. Okay, I run the process and using the okay 1.4 exactly. I hope I have done everything correctly. Now let's see what's going on. Again, since this is going to be a long simulation, I'm just going to show you the starting part, then I'm going to pause the video and all right. Now, as you can see, the steady state level is very much lower. I haven't shown you this time start of the process or how to reach that steady state value. But when we have 1.5 liters per second, this is the steady state value here. And the steady state value here is going to be equal to somewhat like, I think, 12 centimeters. And this is going to be something like 6.5 centimeters. Now, starting with times equals 20 seconds, we drop the outlet level to 1.40. Therefore, we are going to see an increase in water level. And let's see what's going to, or anything is going to differ or not. This is the idea. Let's wait for a couple of seconds. First of all, it seems to me the first tank, of course, we are going to check this, but the first tank is increasing faster, the level of the first tank, which means sooner or later this will be transmitted to the second tank. And with 50 seconds or 60 seconds or 70 seconds, we can see the increase in the water level of the second tank pretty much clearly. Let me wait a couple of more seconds then. Let me not hide this from you also. Okay, the second tank is also significantly increased. Let's see whether I'm just seeing what I want to see, or whether what I see is objective reality. We're going to be checking in a couple of minutes, I guess. So let me first again pause this video. Later, I'm going to meet you at the end of simulation again. Hello again. Simulation is about to be over. It's 590 seconds has passed, and you can probably see that both levels have increased with the red and the blue lines. Now the red line is the second tank is a higher water height here. So in 2 seconds, it's going to be over. 1 second, and the simulation is over. Okay, well, not simulation, but the animation, I may say, is over. Now, if we would like to see the again the output of the second tank, this is going to be the output of the second tank. And if I show on the same figure, I think I call this Y1. Did I call it Y1? Yeah, let me call this one this one the Y2. All right. So let me close all and plot Y1. That was the first response. And that was the second response. So that was at a lower level we were operating, at a higher flow rate outlet flow rate we were operating, and we decreased the flow rate by 1 unit, and we decreased the flow rate by 1 unit in both cases. But to compare them in a more satisfactory manner, what we should do is this. I plot both of them, subtracting from the first value, because the first value is actually supposed to be the initial starting, the previous operating point. So what I do is I subtract from the previous operating point of both responses. And when I do that, I obtain this result. Please note that the same coloring is used for both cases. Y2 is corresponds to the response at the lower water level, whereas this one, the blue one, corresponds to the higher water level. And this is a pretty interesting response, which simply says that KP value has not changed. So steady state gain in both cases is somewhat like close to 2 centimeters over 0.1. So it's going to be 20 whatever the unit I have calculated before. On the other hand, as you can see, the operation at the lower water level is a pretty significantly faster dynamics. I'm not going to show this one again, but I think this is pretty much somewhat like maybe half of this value. So you can calculate, or you can show it on your own, and maybe the same that time, I don't know. One may also show it, but this value seems to have significantly changed. Maybe, I don't know, maybe 100 seconds, whatever. Just calculate on your own. But the point is this: when I only change the operating condition from 1 liter per second to 1.5 liter per second, which corresponds to whatever the steady state values here correspond to. It corresponds to here, this one box corresponds to steady state value of 21.8 centimeters, I guess, and this one probably corresponds to 12 centimeter, whatever. you give a change of 1 unit, I'm sorry, 0.1 liter per second, minus 0.1 liter per second change in the manipulated variable, what we obtain delta y steady state is equal to delta y2 steady state. On the other hand, steady states are equal to each other. Therefore, Kp value seems to be constant here, which is about minus 20 centimeters per liters per second. On the other hand, time constant seems to be pretty much drastically changing. So, well, the first question may be, so what's the big deal, you may say? The big deal is, as I'm going to talk in the second lecture of this experiment, I'm going to try to connect why we try to come up with an empirical model. Now we have two empirical models. So we are going to have two different settings. And the point is, I have only applied this at two different locations. If I have applied this method on different locations, maybe at 1.6 liter per second, I could have applied, or lower than that value, or anywhere between, probably tau would be all times it would be changing. So which tau, and since the Kc and tau I values, the PI controller settings, I'm going to talk about them in details in the second lecture, since they are going to be functions of tau p, and since they are going to be also changing, which means that, in other words, the different ranges of operation. So again, let's think about in physical terms, this is the height of the second tank. When we are here at lower heights, our tau values seems to be smaller, which means the process has faster dynamics. When you change the flow rate here from the first tank, the response seems to be faster. But when we are operating here, or the second tank we are talking about, but also when we are operating at a higher water level, of course, we are operating the first tank at a higher level. And when we change the flow rate, then the response is going to be here slower. Therefore, the optimal, or optimal in quotation marks, PI controller setting seems to depend on the range. So if you just concentrate on a single process model here and come up with a single setting, and you hope that this is going to work for the whole range, you are going to be mistaken. So you have to carefully analyze what's going on, about the limits of the change about tau values, so that you get a better grasp. And there is another thing. So this shows the nonlinearity of the process. It gives a hint about the nonlinearity. There is another thing about nonlinearity. Actually, there is more to do that. For instance, you may ask, what if I change from 1.5 to 0.9? If I change, what's going to happen? Or would the response drastically change? It may. But let's deal with first a much more modest aim. What if I change this flow rate from 1.5 to 1.6? If I had made this change. Now, in a linear process, what we would have obtained would be this red line, but in opposite direction. But this is not a linear process. Strangely, the Kp value seems to be constant, but when we have the same directional change in U values at different height values, at the same height value on the other hand, if we have two different delta U values with the same magnitudes, but at different signs, would we still have the same Kp values? This is the question, and also tau values. Let's also check that. Okay, so this time I'm going to be using, is it 1.6 exactly? Yes, 1.6 exactly. So here, especially for the second simulation, 600 seconds is pretty much unnecessary. About 300 seconds, we have already reached steady state. That's actually another very clear reason why, or indication of the lower tau value. Okay, so what I'm going to do is again simulate the process this time. Okay, let it be again 600. Hopefully you're not seeing this whole long simulation. So let's get rid of those. Okay, and here the animation. There we go. Again at the low value. And now what we do is we increase the outlet from 1.50 to 1.60, but now we have a problem. We may have a problem. Now, since this is about like 7 centimeters, this may drop down to, if it drops down to lower than 4 centimeters, then the process dynamics will change because the outlet flow rate will be equal to 0. So this experiment cannot be performed. Let's see whether this is the case. Maybe it's not going to drop that much, and we can perform this experiment. Let's see. So it's dropping down. I even try to show this as much realistic as it can be, so that it's about, when it's about 4, you are at the same level with the pump. Okay, I think we are about 5. Let me also show you this figure so that you can see whether we are reaching the steady state or not. This is 8. We are close to 4, but not 4 yet. I haven't checked this, so I really not know whether we are going to reach 4 or not. Okay, all right. Again, let me pause the recording and see what's going to happen. Okay, I think we did it. We are just about 4, something like probably 4.5, something like this, because still outlet flow rate is 1.60. We are still above 4. The value 4 is not seen here. Can I change the axis? No. And they seem to have reached steady state. Actually, let me stop this simulation because I already have the values. Okay, I'm going to use the other figure. All right, so this is the response that I obtained previously. And the current response that I obtain is this one. All right. So now the question is, do they overlap? So to see that whether they overlap, what I'm going to do is I'm going to plot negative of the current response, see whether they overlap. No, that wouldn't be the case. I should have subtracted from the initial value. I'm sorry for that. So let me call it Y3. Y2 again. Actually, Y2 minus Y2, 1. All right, hold on, plot Y3, and I need a negative value, so it's plus. Okay, that's very good. Now, tau seems to be constant. However, Kp value seems to be higher. Well, actually, I'm not very sure because, well, it's just because of due to luck, maybe that single value. Here, maybe I should have used something like this. It is going to be better. Let me use it, a more reliable method. Now, instead of this value, I'm going to be using the first, I'm going to using the average of first 20 values, because during that time, it was the same operating condition. Okay, so it pretty much guarantees that the initial condition is very close to 0. And this is mean from 1 to 20. Okay, now I think this is better. Yes, when I draw it that way, so it was just noise. As one can see, it is strange that here again we have the same Kp value, but the dynamics here seems to be even faster. So again, even a smaller tau value here for this specific case. All right, so well, now I'm not going to find the tau exact value, but I can see that I think 20 it's probably as low as it is 100 seconds. But Kc seems to be constant here. Okay, so there may be other things that you would like to try. You may change, as I said, from, for instance, 1.6 to 0.9. If you decrease the whole thing, what's going to happen? Will it be like the response that you would obtain by changing by one step, by 0.1 changes, if it's not a linear system that you may not have? But what I'm trying to say is that in the first part of this modeling part or understanding dynamics part of the experiment, it is up to you to conduct a couple of experiments and obtain a couple of reaction curves, so that you can characterize the dynamics of the process. So you may have a set of Kp and tau values, so that you get a grasp of how much these values may be changing, so that later you are going to be more comfortable in determining the quantum settings here. So let me go back here again and see whether have I missed anything related with this part. Let me see. All right, I kind of talked about these. I think, yes, closed loop under servo control. I think I pretty much talk up to the fifth part.